feeble-minded fools having fun. I'll do something about that. Witness the power of real radicals!
Something crazy just happened. The crowd is losing its mind, and not in a good way.
Attention everyone, for your safety, I need you to calm down. I repeat, calm down. Now don't let these radicals kill the flow. Just simplify them, then on with the show. First, we're going to understand what a radical is. Unfortunately in math, especially algebra, they're nowhere near as cool as an actual rock band. But if you ever have to deal with math radicals, understanding how to simplify them becomes smooth sailing. A radical expresses the root of a number or expression. Its symbol is this checkmark-looking sign that I'm sure many of you have seen plenty of times. A radical's general form looks like this. N is called the index. It just tells you the degree of the root. And A is the radicand, aka the number or expression that we are taking the root of. In this video, I'm going to call the radicand the subject. The most common radical is the square root. It automatically means that the index is 2, except that the 2 is invisible. Therefore, it's automatically known that the square root symbol by itself means that the index is 2. When dealing with cube roots, the index is 3. With fourth roots, the index is 4, and so on and so on. From 3 onwards, the index sign is visible with the radical symbol. But, for the sake of preserving sanity, I'm just going to focus on square roots. Index 2 only. Now, let's discuss what is called the perfect square. When dealing strictly with numbers, we have our perfect squares like 1, 4, 9, 16, 25, 36, etc. They are considered perfect squares because when square rooted, we get a whole number like 1, 2, 3, 4, 5, etc. This also applies to negative whole numbers. The result of a negative number being multiplied by itself gives you a perfect square. However, for now, we're not going to bother with negative values. No negative subjects, no negative results. We'll look into that another time. Positive vibes only. So, for the entirety of this video, you're going to see an unknown variable stating that it's greater than or equal to 0. Statements like these are called domains or ranges. In algebra, the domain tells you the values you can put into a formula, and the range tells you the values you can have come out. In the case of this radical video, the domain, aka the subject values going into the formula, which is x, will not be negative. Therefore, x, or any other variable letter used, will be greater than or equal to 0. Same with the results, which is y. We're not interested in negative values for now, so that means y will be greater than or equal to 0. Alright, so what happens when you're no longer dealing with a perfect square? Let's take the square root of 20 for example. When dealing with a value that is not a perfect square and trying to simplify it, the main thing to ask is, does it have a factor that is a perfect square? In other words, can it be divided by a number that is a perfect square? So, with the number 20, here are all its factors. In this case, the factor that is a perfect square is 4. What that means is, the the square root of 20 can be written as the square root of 4 times 5. We can also give the number 4 and the number 5 their own radical symbol. Since 4 is the perfect square, its square root is 2. The square root of 5 stays how it is. It is not a perfect square, and it does not have a factor that is a perfect square. A quick note. Yes, the number 1 is a perfect square, but factoring it out doesn't change anything. So that means it's always ignored, and therefore, 2 times the square root of 5 is the simplified version of the square root of 20. Let's now look at the square root of 11. Does it have a factor that is a perfect square? In this case, the answer is no. So, the square root of 11 is as simplified as it's going to be. Nothing can be done to it. Now comes the fun part, when we start throwing unknown variables into the mix. The same rules that apply to numbers are the same rules that apply to unknown variables. Now, before I continue, if you're not fully confident with algebra and exponents, information will be posted below. Here we have the square root of x squared. Since x squared is a perfect square, its square root is x. Anything squared, or to the power of 2, is a perfect square. The square root radical pretty much just cancels it out. So what if we have the square root of x to the power of 3? What can we do to simplify that? Well, the same question has to be asked, which is, does x to the power of 3 have a factor that is a perfect square? The answer is, yes it does. X squared is a factor that is a perfect square. So that means we can write the square root of x to the power of 3 like this. The square root of x squared times x. Each subject can have its own radical symbol to give the square root of x squared times the square root of x. The square root of x squared is just x, and the square root of x cannot be simplified any further because it does not have a perfect square factor. Therefore, the square root of x to the power of 3 is x times the square root of x. Let's make it more interesting and use a product subject of 2 variables being square rooted. We're going to simplify the square root of x to the power of 3 times y to the power of 4. The easiest thing to do is to start with simplifying each variable individually. Now, before I continue, be very cautious of the subject with a few simple rules. When the square root of 2 or more subjects are a product, aka they are being multiplied, and/or the subject is a quotient, meaning being divided, that will allow us to split each subject into individual parts with its own radical symbol. That means the square root of a times b is equal to the square root of a times the square root of b. Likewise, the square root of a divided by b is equal to the square root of a divided by the square root of b. With that being said, however, the square root of a plus or minus b is not equal to the square root of a plus or minus the square root of b. When the subjects being square rooted are sums and/or differences, each value does not get its own radical symbol. The subjects in this case stay unchanged. The best way to prove and understand math rules is to use simple numbers. Let's say a is equal to 4 and b is equal to 9. The square root of 4 times 9 is equal to the square root of 4 times the square root of 9. This gives us 2 times 3, which is 6. Alternatively, the square root of 4 times 9 is the square root of 36. And the square root of 36 is 6. Now consider the square root of 4 plus 9. If we try to write it out as the square root of 4 plus the square root of 9, that would give us 2 plus 3, which is equal to 5. But the fact is, the square root of 4 plus 9 is equal to the square root of 13. As you can see, the square root of 13 is not equal to 5. Here we have a as 100 and b as 4. We are going to calculate the square root of 100 over 4. Since 100 over 4 are values being divided, we can write it out like this. Based on the rules, you can see that both the 100 value and the 4 can have their own individual radical sign. So the square root of 100 divided by the square root of 4 becomes 10 divided by 2, leading to an answer of 5. Simultaneously, if you calculate the square root of 100 over 4, that gives you the square root of 25. This also results in the answer being 5. Now, let's say we have the square root of 100 minus 4. If we try to write it out as the square root of 100 minus the square root of 4, that would lead to an answer of 10 minus 2, which is 8. However, the true calculation of the square root of 100 minus 4 is the square root of 96. Therefore, as you can see, the square root of 96 is not equal to 8. Once you understand these basic rules, simplifying with radicals will be light work. All right, let's go back to our expression, the square root of x to the power of 3 times y to the power of 4. We can break the subject into pieces and give each variable its own radical symbol. Now we treat each value individually and simplify. With the previous example, the square root of x to the power of 3 gave us x times the square root of x. For the square root of y to the power of 4, we break it down into the factors that are a perfect square. So we can write it as such. The square root of y to the power of 4 is equal to the square root of y squared times the square root of y squared. Now we can cancel out the radical sign with the 2 exponent to get y times y. Once we have all the values simplified, we then bring them all together by multiplying. So that's x times y times the square root of x. This results in an answer of y squared times x times the square root of x. Think of this entire process of breaking the radical expression into pieces, simplifying each piece, and then bringing them back together. Let's now have a look at this expression. This time, we'll have a number and 2 variables as the radicand. Since the subject are 3 values being multiplied, we can write it out like this. We have the square root of 32 times the square root of x squared times the square root of y to the power of 3. Next, simplify each radical piece. So, with 32, find a factor that is a perfect square. In this case, the number 16 is a value that applies. The number 4 is also a factor that can be used too, but it's a lot easier to use the largest factor that is a perfect square. With the square root of 32, we can break it down into the square root of 16 times 2. Since multiplying, we can get the square root of 16 times the square root of 2. The square root of 16 becomes 4, and the square root of 2 stays as it is to give us an answer of 4 times the square root of 2. Now we can move on to the square root of x squared. The radical simply cancels out the 2 exponent and gives us x. With the square root of y to the power of 3 piece, we now break it down with its perfect square factor to get the square root of y squared times y. Break it up to get the square root of y squared times the square root of y to result in y times the square root of y. Now that we have all the radical pieces simplified, let's get the final result by bringing them all together. That's 4 times the square root of 2 times x times y times the square root of y. When multiplied, the final result is 4xy times the square root of 2y. Here, we're going to take a look at the square root of y to the power of 4 over 16. This time, our subject values involve division. Therefore, we can write it out like this. So again, we can break this expression down into radical pieces. Starting with the square root of y to the 4, we can write it out as the square root of y squared times y squared. The radical symbols cancel out the perfect y squares to give us y times y. That leaves us with a numerator of y squared. As for the denominator, the perfect square that is 16 becomes 4. Now put the simplified pieces together to get a final answer of y squared over 4. Now, onto this expression. That's 2 times the square root of x plus the square root of 9x. After discussing the rules based on operator signs, some of you might have looked at the example and thought, oh, looks like we're adding. Nothing to change here. The good news is you're thinking on the right path. However, it's very important to be mindful of if we're adding or subtracting subjects under one radical versus adding or subtracting separate radicals. Let's unpack that by revisiting the sum difference rule. As mentioned previously, the square root of a plus b is not equal to the square root of a plus the square root of b. Take note that the square root of a plus b are two added subjects under one radical, whereas the square root of a plus the square root of b involve two separate radicals being added together. It might seem a bit overwhelming, but feeling that way is normal. You'll get the hang of it, I promise. So, let's first take a look at 2 times the square root of x. Can it further be simplified? The number 2 is just a coefficient, so that stays as is. What about the square root of x? Does it have any perfect square factors that it can be divided by? In this case, the answer is no. What that means is 2 times the square root of x stays the same. There's nothing that can be done to it. Now, what about the square root of 9x? Since it is a product within the radical, we can write it out like this. And since 9 is a perfect square, we end up with 3 times the square root of x. Just like previously, the square root of x stays as is. Therefore, the entire example can be written as 2 times the square root of x plus 3 times the square root of x. Is there anything more that can be done, or is simplifying complete? For those of you who noticed that more can be done, you are correct. Both added expressions have the like term, which is the square root of x. Therefore, we can add them together to get 5 times the square root of x. The process of combining like terms also works with radicals. If you're not too confident with combining like terms, a link will be posted below. When combining like terms with radicals, the subjects must all be the same variable. Let's say we had 2 times the square root of x plus 3 times the square root of y. Since both variables are different letters, they are not like terms. Now what about 2 times the square root of x plus 3x? Yes, both the variables are the same letter. But the square root of x and x are not like terms. Therefore, a like term with radicals equals the same letter variable and the same radical symbol being added or subtracted. Here we have the square root of a to the power of 5 divided by 5. Since the subjects involve division, the expression can be written out like this. First, we'll focus on the a to the power of 5 piece. When we break down a to the power of 5 with a perfect square factor, this is what we get. I'm sure by now you get the pattern. If not, that's okay too. So, to break down a squared times a to the power of 3 further, we get a squared times a squared times a. The square roots of a squared become a, and the square root of a stays as it is. Multiply a times the square root of a to get a squared times the square root of a. Now that the numerator is complete, onto the denominator, which is the square root of 5. Since the number 5 does not have any factors that are a perfect square, we don't do anything to it. The square root of 5 remains as it is. Now, we bring the pieces together to get a squared times the square root of a over the square root of 5. We're done, but the denominator is a radical. There's no problem, really. The answer is correct. Typically in math, though, radical denominators are avoided. Consider this. If you were sharing that sandwich, would you rather divide it by 2 or the square root of 2? Of course, it's much easier to pick 2 as the option. Same thing applies with dividing with radicals. It's often easier to remove the radical from the denominator even though it's not required. So how do we do that? The next step is to rationalize the denominator. Don't worry. It's easy. It sounds like a big task, but it's a small move. But first, let's briefly go over the meaning of a rational number versus an irrational number. A rational number is either an integer, like the number 2, a value that has a decimal and the numbers after the decimal come to an end, an example being 1/2 or 0.5, or a rational number is a value that has repeating numbers after the decimal, like 2/3. 2/3 results in the number 6 being a repeating number after the decimal. All numbers that are not perfect squares are irrational numbers when square rooted. Why? Because when calculated, we get non-repeating numbers after the decimal that go on forever. Let's say we have 1 over the square root of 2. All you do to rationalize with a radical denominator is multiply the numerator and denominator with the same denominator value. So, if you have 1 over the square root of 2, you multiply the whole thing by the square root of 2 over the square root of 2. That gives you the square root of 2 over 2. The value of the expression remains the same because the square root of 2 over the square root of 2 is equal to 1. And that's pretty much it. A square root radical multiplied by itself cancels out the radical symbol and gives us a rational number in the denominator. Now, let's apply this method of rationalizing the denominator to the answer a squared times the square root of a over the square root of 5. Just rationalize it by multiplying it by the square root of 5 over the square root of 5 to get a squared times the square root of 5a over 5 as a final result. Alright, here's an example, the square root of x over 27. Since division is taking place, we can separate the expression into radical pieces. Writing it out, we get the square root of x divided by the square root of 27. Now time to simplify. Again, x has no perfect square factors, therefore the square root of x stays the same. With the number 27, its perfect square factor is 9. So we can write out the square root of 27 as the square root of 9 times 3 and give each number its own radical, resulting in the square root of 9 times the square root of 3. The square root of 9 is 3, and the square root of 3 stays as it is. Therefore, the square root of 27 is written as 3 times the square root of 3. Now put the pieces together to get the square root of x over 3 times the square root of 3. Since we have an irrational denominator, we multiply the numerator and the denominator by the square root of 3. The square root of x multiplied by the square root of 3 becomes the square root of 3x, and 3 times the square root of 3 times the square root of 3 becomes 3 times 3, which is 9. Therefore, the final result is the square root of 3x over 9. Now, consider this expression, 2 over the square root of 5x. This time, we have an unknown variable in the denominator. The square root of 5x stays as it is because 5 and x do not have any perfect square factors. With rationalizing the expression, we simply do the same thing with numbers as with unknown variables. Here we multiply the entire expression by the square root of 5x over the square root of 5x. That gives us a final answer of 2 times the square root of 5x over 5x. Now, check this out. Here we have the square root of 7 as a number radical in the denominator. But this time it is part of a binomial. Interesting, isn't it? I promise, we're almost done. The show will go on. Just like mentioned earlier, radical denominators are okay, but they still aren't preferred. So with this example, we're going to rationalize the square root of 7. To do that, we're going to use what is called the conjugate. The good news is, the definition is much easier than it sounds. A conjugate is formed by simply changing the plus or minus sign between two terms. In other words, the signs change while everything else stays the same. Let's look at some examples. The conjugate of a plus b is a minus b. The same applies to the other examples. Their conjugates are just opposite plus or minus sign. See, pretty straightforward. Okay, so why does this matter? The whole point of using conjugates is to use the difference of squares rule to rationalize. Here's how that works. The conjugates a plus b times a minus b result in a squared minus b squared. That formula is the difference of squares. If you're not too sure about the difference of squares, links will be posted below. Taking the same principle, the square root of a plus the square root of b multiplied by its conjugate results in a minus b. The square root being squared is cancelled out, giving us a rational number. Conjugates represent same terms, opposite signs, total cancellation. Let's revisit the example. The conjugate of 4 minus the square root of 7 is 4 plus the square root of 7. Now take the conjugate and multiply the numerator and the denominator with it. The numerator becomes 3 times 4 plus the square root of 7, and the denominator becomes 4 squared minus the square root of 7 squared. 4 squared is 16, and the square root symbol is cancelled out to give 7. That gives us a denominator of 9. This gives us an answer of 3 times 4 plus the square root of 7 over 9. Here we can simplify further by dividing the numerator and denominator with the common factor 3. That results in a final answer of 4 plus the square root of 7 over 3. We're fully simplified with the rational denominator. Now, of course, this wouldn't be a complete lesson without algebra and conjugates. Here we have 1 over the square root of x plus the square root of 2. As you can see, the binomial denominator has two radicals we can rationalize. All we do is use the exact same process. The conjugate of the square root of x plus the square root of 2 is the square root of x minus the square root of 2. So we multiply the numerator and the denominator by the square root of x minus the square root of 2. The numerator becomes the square root of x minus the square root of 2, and the denominator becomes the square root of x squared minus the square root of 2 squared. The square roots are cancelled out, leaving a denominator of x minus 2. Therefore, the square root of x minus the square root of 2 over x minus 2 is the final answer. And I think we can end it all here. So, let's briefly go over the entire lesson when presented with simplifying square roots, especially with algebra. First, look at the radicand/subject and understand if it follows the product quotient rule and/or the sum difference rule. If using the product quotient rule, split each number or variable into pieces. Then simplify each piece, then bring them back together. Lastly, if your radical is in a denominator, consider rationalizing either with a single radical term or a conjugate. This video was powered by my favorite coffee, green matcha. If you got any value from this lesson, refills are always appreciated. Otherwise, please comment, like, share, and subscribe. Well, that's a wrap. When the show is done, you all get to study it.